Welcome, all of you guys. Great pleasure to talk to you on this fine Saturday morning. It's not that fine here, actually. But anyway, so I'll just, the topic is the human brain. And I've struggled with this topic for the last 2 or 3 years that I've been doing these sessions because it's quite a vast area. And I'm trying to talk about various aspects of it in 1 hour or 2 hours is actually quite hard. So I think what we'll do is I'll talk a little bit about some aspects of it, which I think is important for you guys to know about. But the rest of it, I think we should do as an interactive. So I'll just stop in between and you can ask me questions and we can have a discussion. I think that probably works better that way. Okay. So just to introduce myself, my name is Rajiv Mohanraj. I am from Alleppey in Kerala. And that's a school I went to, Vidyadhiraja in Alleppey. And for your level, 11 and 12, we had something called pre-degree back in the day. And I went to this place called UC College in Alleppey. And after my pre-degree, I went to Medical College in Alleppey and completed MBBS in 1994. And since 98, I've been living in the UK. So that's where I live now. That's a map of Britain, and that's the city of Manchester. You can see right in the middle there. That's where I live. Just a little bit about this place, Manchester. It's regarded as the birthplace of the Industrial Revolution. This is where heavy engineering, the big cotton looms and things like that first started being made at the birth of the Industrial Revolution. And that heritage still exists. There's a long tradition of science and technology here. This is J.J. Thomson, who first split the atom at the university here in Manchester. It is also the home of a lot of liberal thought. So the Guardian newspaper, which is one of the beacons of progressive and liberal thoughts in the world, started in Manchester. It was called the Manchester Guardian until 1958 when it relocated to London. It is also home to Manchester United, which is about 3 miles from my house, and we had a season ticket for a number of years. We gave it up. Those are my children at Old Trafford watching the game. There is also another football club in the city, but we won't talk about that. They're not so good. Good. Okay. This is where I work. I'm a neurologist and I work in this hospital. And I also teach and do research in the other place, the University of Manchester. I'm called an honorary senior lecturer. The honorary bit means that they don't pay me, but I do stuff there. Good. Now, a few words about GrainEd. Now, you may already know this because I know you've had lessons from other mentors, but it is conceived as an alternate education platform, and it is not to replace what you learn at school, but to be complementary to that, to set the knowledge that you acquire in school in the right context. So you know why you learn what you learn and how that's going to be applied in your life in the future. And the idea was to get professionals like myself and everybody else in different fields who use that knowledge in their day-to-day lives. So you understand what it is that we seek to gain, and to go from what is known, at your current stage, or it might be the level of knowledge might be zero, it might be a little bit, it might be quite a lot. But then from there, how do you go to new things? How do you discover new things? And that approach to acquiring knowledge is the root of all of scientific progress in recorded human history, really. So I think it's important to understand how we got to where we are. So that's really one of the whole ideas, and how to integrate that knowledge. I mean, we don't exist in silos. We are not in little specialized pockets of mathematics or chemistry or social sciences. They're all integrated into one overarching philosophy of knowledge, and that's kind of the whole idea. And you should be able to enjoy it because it's quite fun. It's really cool stuff, that learning stuff, knowing about it. It really brings pleasure. So that's really what we want to try and communicate, because we as a group of people who got together with this idea have had these experiences over the years, and we just want to try and pass that on to you. And it is completely universal and completely free. Anybody can join. This is a website. You hopefully have been on it, but if you haven't, please go to GrainEd.com. It's got all the details of courses and sessions and material and gallery and so on. So it's a great website, so please have a look. Right, so here's a topic at hand, the brain. What is this thing? I mean, it's the seat of all of our experience. We see, we hear, we think, we feel, we move, we perform very skilled tasks, we play games, we can hit a moving ball at a great speed, all of it because of stuff that's going on in the brain. How does this happen? And what is the fundamental units that make it happen? And how did we discover all of those things? And what are the things that remain to be discovered about how the brain works? So those are the sort of areas that we would want to talk about a little bit today. So I'm going to, the plan is to do this over 2 sessions, right? So I'll do a little bit, maybe 40 minutes or so today, and then we'll have a little discussion and maybe meet again in a week's time and go through things again, maybe a little bit. Good, okay, right. So what is the brain? How many people have actually seen a brain? You can type something in the chat. You may have seen it in an exhibition, maybe in a museum or in your science lab, and you may have seen a model. I'm not even sure this is a real brain, actually. It looks a lot like a model. But essentially, this is what it looks like, yeah? How many people have seen a brain? Anyone seen a brain? Just a model, okay. Yeah, that's fine. But essentially, this is what it looks like. And you can see that it is really wrinkly. It's been folded up and squeezed tightly together to get it to fit into our skull. So in a sense, it is actually a bit too big for our heads. So it's a hugely overdeveloped organ in what is essentially an average size primate, which is us. You know, we are apes. We are not particularly big apes. I mean, we are bigger than monkeys, but we're not as big as gorillas. And so for the relative size of us, this brain is quite big, and it is folded up to try and fit it into our heads. It has got 100 billion cells at an estimate, which are called neurons. These are brain cells, and between them there are between 100 and 1,000 trillion synapses. So synapses are the connections between brain cells, and that's how they communicate with each other, through these junctions, these connections. There's 100 trillion of them, and it's also just the most amazing thing. And how does this thing produce all of our sensory experience of the world? How does it produce all of the skills that human beings can do, all of our thoughts and emotions and ideas and the works of genius and everything else? So, well, are we that different to animals? Well, when you look at the brains, it's actually not that different, you know. So if you look at this, the brain of a chimpanzee down here, okay, the human brain looks a little bit more folded up, so maybe there are more cells and more connections within the human brain, but to look at it, it looks not that different. And if you just look at the number of folds of the brain and the size of the brain, the dolphin maybe has a better brain than humans. If you go to lower life forms, rhesus monkeys and rats, you can see the folding is not that prominent. So maybe it is not a little bit smaller, maybe fewer cells. But there are commonalities. You can see that the structure looks pretty similar, right? So how do we go about understanding this? Does anyone have any idea of how we might understand the brain? Any idea from what I've said so far? Anything in the chat? Through the model, through the nerves. Okay, yeah. So what is a good model then, Dennis? How would you, I mean, you can't really take a brain out of a person's head and study it. Obviously, that would kill them, and you can't really kill people, although there have been murders committed in the name of studying science and things like that, but that's generally not possible. So what's the best model for the human brain? Well, I just showed you some pictures of animal brains, didn't I? And you know, that could be because they have, as I said, even though the human brain looks a bit bigger and maybe has more cells, there are commonalities. So we can study animal brain. So that's one way of animal brain, understanding the brain, study the brains of animals. You can cut up a frog or it's even something even smaller than that, and understand what the brain cells do and their connections. And you can even make them have diseases. You can so you can study the animal brains in health and disease. And so these are the commonly used animals to study the brain function. So mice, sometimes rats, even smaller, zebrafish is a very widely used model for studying the brain. And even simple, one of my close colleagues here in Manchester uses fruit flies, and fruit flies have very small nervous systems with very specific numbers of cells, which can be manipulated. So you can change their connections and things like that and understand exactly what happens to the nervous system. And these people are called neuroscientists. Okay, so people who study brain by using these models are called neuroscientists. Now, the other way to study it is to see what happens when the brain goes wrong. Okay, so what happens when the brain has a disease. Now, do you know about brain diseases? Anybody want to volunteer some suggestions on brain diseases? Have you come across any brain diseases? Okay, we've got a few in the chat. Brain death, Alina says. Brain tumor, says Hilal. Meningitis, Alzheimer's. Yeah, these are all brain diseases. Excellent. So these are all conditions that affect the brain. And when that happens, the brain goes a bit wrong. And we can see what happens to that person when the brain has gone wrong. And then we understand a bit about what the brain normally does, depending on what's happened to it. So you're quite right. All of these things. So very commonly, you have paralysis because of a stroke. It's very common. So there is damage to one part of the brain because of loss of blood flow, and there is weakness down one side of the body, or you lose the ability to speak or see. And that then you understand what that bit of the brain was normally doing before this happened to that person. Then there is epilepsy. Have you come across epilepsy, where people have fits or seizures, and dementia, or memory loss? So these are bits where these are conditions where the brain goes wrong, and when we study those people, we can understand something about what the brain normally does. And people who do that are called neurologists, and I'm one of those. So that's my way into understanding what the brain does. There's another way. I mean, it's not just when the brain goes wrong. What about normal brain activity? How do we do the things that we do day to day when things are going fine? Okay, so can you tell me a few things that you do with your brain on a day-to-day basis? Normal functioning, thinking, solving problems, thinking. Yeah. Anything else? You guys are students. Alina says hunger. Hunger is something that you feel. Yeah. And it is your brain telling you it's time to take in some nourishment. Yeah. Anything else? Understand emotions. Yeah. Responses. Yeah. All of these things. These are all things that we use our brains for. This is normal day-to-day stuff. This is how we understand all of these senses. Yeah, sight, smell, hearing, everything. And so yeah, so memory. Yeah, how do we learn and remember things? How do we feel emotions, love? When people fall in love, they say they invoke a lot of things. They say it's my heart, and in fact in Malayalam we call it a karale, and it is actually the same word in Hindi, jigar, mere jigar. So that karal and liver, jigar are the liver. I mean, love's got nothing to do with the liver, okay? And it has got nothing to do with your heart either, even though your heart might go faster when you see the person you're in love with. It's actually a bunch of stuff that's happening in your brain. So all of this experience of our day-to-day life is to do with the brain. And yes, you can study those things. And people who study that are called neuropsychologists. And they do various experiments, measure various aspects of brain functioning to see how the brain does these things. And we are at the very foothills of the understanding of how the brain actually generates these sensations. And I'll talk a little bit more about that in the second session. Good. Okay. So that's a kind of basis of how we go. And from my point of view as a neurologist, I understand the brain through studying a disease. Fits. Yes. That's right, Alina. It's a fit. It's a seizure. Okay. Can I ask, what did you feel when you saw that? Anybody? What did that video make you feel? What was your initial reaction to seeing that video? Did you feel okay? Were you not bothered? Or did you feel anything else? Any kind of emotion? Yep. Yep. You felt sad for her. Okay. Anything else? If you were if that was your friend and you were just sitting with her and that happened to her, what would be the initial reaction? No? Yeah. Accept panic. Yeah. Yeah. It's call someone. Yeah. Scared. Yeah. Yeah. Keep going. So these are all very common reactions to people who are seeing it for the first time. Yeah. You feel scared. You panic. You want to help her, but you don't know how. And this feeling of being scared and this of helplessness and so on is really where we start from when we try to understand this disease. And when people first, I mean, this has always happened. This is something that that all life forms have, these seizures and fits. Animals have it, dogs have it, cats have it, and human beings have always had it. And ever since people started writing down history, there have been recordings of this. And the initial thought was this was something unnatural. There was something going on. This was possession, bada. In Malayalam, you call it preda bada or something like that. So the first descriptions were, well, this is where human civilization first started, okay? About 1700 years before Christ, around the valley of Euphrates and Tigris, the so-called Mesopotamia. That's where human beings first settled down, started an agrarian civilization and settled and lived as a community. Before that, they were hunter-gatherers. They were wandering around in tribes. And when they started writing stuff down, this is the initial descriptions from Babylon, and they describe things as this was a description of someone having a seizure or a fit, described as the demon pouring out of them, and the exorcist asks them to repeat a prayer, and eventually the demon lets him go. So this was seen as a spirit or the devil, or even an evil god possessing the person. Now, this carried on until the Greek civilization. So about 400, 500 years before the time of Christ, there was this guy called Hippocrates. Has anyone heard of Hippocrates? Yes. Yeah, so he's the granddaddy of all doctors in the world. Yeah. So when you join medical college or you qualify as a doctor, you swear an oath, and it is called the Hippocratic Oath. That's the thing that this guy came up with. And he's considered the father of medicine, really. And he said, no, this is not a divine or sacred disease. It's got a natural cause. And people just say it's divine or sacred because they don't know what they're talking about. And because it looks a bit strange, they think it is some kind of otherworldly phenomenon. And he also said that people, those who attribute a sacred character to this malady were like the magicians, purifiers, charlatans, and quacks of our own day. Now, he said that, 2,500 years ago. That's still the case. People still consider that. There are many parts of the world where epilepsy is considered a demonic possession and things like that. And then you have this period where, so the idea that these are charlatans and quacks is still true to a large extent. It was mentioned in the ancient Indian text, the Charaka Samhita and Sushruta Samhita. It was called apasmara. Okay, smarana is memory. So apasmara is loss of memory. So you basically have a period where you go unconscious, you have no idea what goes on, and you come around, you have no memory of what happened. So that's why it's called apasmara in Indian languages. And it was described as an imbalance of the doshas. So the three doshas of Vata, Pitta, and Kapha. And if these things are not in balance, you get all these various diseases. The interesting thing is, around the same time, the Roman civilization, the Roman Empire was in its pomp. And the great doctor of that era was this guy called Galen. And Galen came up with the idea of the four humors of blood, yellow bile, black bile, and phlegm. So we talked about in the Indian context, Vata, Pitta, and Kapha. So what is bile? Anybody? Any idea? No? Well, bile is Pitta, right? So and phlegm is kapha. So essentially, this shows you that these civilizations came from a common root, or possibly had a great deal more in common than we think. We might think that ancient Indian culture was completely insular and it had its own cultural roots, but no, these things had a lot of, there was a lot of intercourse, there was a lot of interaction, and maybe possibly originated from the same source. So it's an interesting thing when you think about how ancient people in such distant parts of the world understood the same things in the same way. And Galen was also the first person to say the brain has got something to do with it. The brain is where all your thoughts and the soul is what he came up with. Then we had the Middle Ages, when all the knowledge of classical antiquity, of Greek and Roman periods, was lost. And the church, the Catholic Church, dominated and controlled all activity. You had to think like it said in the Bible, otherwise you were in trouble. So it's a dogmatic position. You cannot question that. You know, God created the earth and everything in it, and everything that you get is just God's will. You have to accept that. And illness is a form of punishment from God. You can't go looking for it, a cure or anything like that. And if you went against that, it was heresy. It was to deny God, and that will be punished severely. You'll be put to death. So in that time, this is from the Bible, and this basically says that Jesus cured somebody who was having a seizure by rebuking the foul spirit, saying unto them, "Thou deaf and dumb spirit, I charge thee, come out of him and enter no more into him." And the spirit cried and rent him sore and came out of him, and he was as one dead, in so much as I said he is dead. So this is going back 1,000 years to the period before Hippocrates, to saying that what was happening was due to demonic possession. So this was a retrograde step, and this is how a dogmatic belief system can lead to loss of knowledge and loss of progress. And that's one of the key things that we should bear in mind, that dogma is the enemy of acquiring knowledge. Then came Renaissance. Now, have you heard of this period, Renaissance, Navodhanam in Malayalam? This is the rebirth of learning in Europe. It started from northern Italy in a place called Tuscany, Florence, and it was some rich people started to explore their own past and rediscovered the Roman and Greek writings. And during that time, during the Middle Ages, where European thought had completely come to a standstill, it was Arabic and North African scholars who were adding, with Indian contributions to things like mathematics, Aryabhatta and so on, that the knowledge had moved on, but it was picked up again by Renaissance scholars. And it was during this time that the vernacular languages of Europe, that's German, French, and English, started developing their own literature. People started writing books, and the first European universities were established around this time. And it is around here that people started discovering what exactly was going on, that there was electrical activity going on within the body, within the nerves, and within the brain. And the first major contribution was by this chap Galvani. Have you heard of Galvani? Anybody? Any? Does that sound familiar? Galvani? Yeah. What did he do? Okay. Well, there's a thing called galvanometer, which you may have heard of in physics. Yeah. So Galvani was he had no interest in electricity, but he was an anatomist. He was studying a frog. So he cut up this frog, exposed its nerve, and was dissecting it. But it was on a metal table, and he left it with the metal forceps touching the nerve. And then there was a spark of electricity, and the leg of the frog, of this dead frog. It was just a dead frog, and it twitched. Checks the presence of current. Yes, that's correct, Alina. Very good. And so he just happened to notice that there was an electric spark, and that caused the leg of this dead frog to twitch. And so, well, there must be some electricity going on in the nerves, because at that point nobody knew what nerves were for. At least when you cut up arteries and veins, you could see that there was blood in it, but nerves, nobody knew what it was for. And then Galvani suggested maybe nerves carried electricity, not fluid or gas. So he did these experiments. So essentially he had these two metal probes, one made of zinc, the other made of copper, connected to two parts of the frog's nerves, and that caused it to twitch. And he wrote this down, he published it, and it went to this other guy called Volta. Have you heard of Volta? Alessandro Volta. He was in Pavia, which is about 200 miles away from Bologna. You have heard of Volt. Yes. Well, yeah. So what's the difference between, everybody has heard of Volta. He's the guy who came up with the idea of, we call electricity voltage, don't we? Because of him. And so he read about this. He was a leading expert on electricity in Italy at the time, because people had demonstrated, Benjamin Franklin had demonstrated that lightning is electricity. The way to capture a static electric charge in something called the Leyden jar had already been described. So he was doing experiments with this, and there is electricity in animals. That's a bit strange. So he did the exact same experiments as Galvani did. And he found that he could get the dead frog's muscle to twitch by connecting two different metals separated by a liquid, and he called it galvanic stimulation. And by doing that, he came up with the idea of putting two different metal electrodes into an electrolyte solution and thereby generating an electrical current. He called it, this is called Volta's cell. And if you add a whole bunch of them from, in a stack, it was called the voltaic pile. This is the first battery. So this is how the first battery was invented, by communication between two completely unconnected fields of science, by someone who was studying the frog's anatomy and another person studying electricity. So this scientific communication, in those days it would have taken months for Galvani's experiments to be written up in a paper and then put on a horse cart or something and drawn all the way to Pavia, and for Volta to read it and then try and do those experiments himself. Now it is instantaneous. You put something on Twitter, you get an instant response, and scientific communication and collaboration is in a completely different universe compared to that time. So this is an instance where you think outside of your own little narrow area of specialty, and you come up with these incredible insights. And then animal electricity from then on entered the public conscience in a big way. Do you know who this is? Anybody? So this is from 200 years ago, 202 years ago. That is it. That's Frankenstein. Yes, this is Mary Shelley's character, Frankenstein's monster. The idea, so the idea that all you need to bring something to life is to pass electricity through it. The idea that electricity was the life force, that you could take a dead body, pass electricity into it, and it'll come alive. And that idea is obviously not true, because you can't bring the dead people and animals back to life. But there is a grain of truth in that, which we'll hopefully explore a little bit further in the next few minutes. And then, so people started thinking of the brain as a battery in the same way that nerve cells are electrodes, like in Volta's cell, and the blood that flows around it is in some way like the electrolyte solution. And this chap, Robert Todd, was a proponent of that idea, and he was heavily influenced by Michael Faraday. This was in London in the 19th century. And London in the 19th century was the epicenter of all intellectual activity in the world, because that was the height of the British Empire, and the Royal Society was making huge contributions. And Michael Faraday was a superstar scientist of that time. He'd come up with the dynamo and the way to generate electricity. And so that was the main turning point, in a sense, of understanding how the brain works. But it was another 50 years or so later that someone managed to prove that there was electricity in the brain. And this was this guy, Hans Berger, who was a German psychiatrist. In the First World War, he was, and in those days, there was compulsory military training, military conscription, so he had to go and fight in the war. And he was on a horse, and he was thrown by his horse, and he fell under a carriage and was nearly run over. And at that point, when he screamed out, he wasn't killed, obviously, but he broke his leg, and he was in the field hospital, and he got a letter from his sister saying, "I had a dream that you fell off your horse and broke your leg." And he wondered how this experience had transmitted itself from his brain to his sister's brain, and wanted to research extrasensory perception. And he was trying to record something like maybe radio signals or something like that that might be coming from people's brains. So he modified an ECG machine and an electrocardiogram that was used to record the electrical activity of the heart, which had been invented at that stage. He did some tweaks to it and eventually managed to record some electrical signals in the brain. Obviously, they are not transmitted across space to someone else's brain, but recording electrical activity using this machine 90 years ago now, really, or nearly 100 years. And because he was a bit of a crackpot, nobody paid any attention to it for about 10 years. But eventually people picked up on it and became a very useful tool. And now it's something that I use every day in my working life. This is my main way of assessing people who have things wrong with their brain. And so we stick some wires onto people's heads on those places, and we connect it to a computer, and it gives us a reading of the electrical signals to the brain, which looks a bit like this. And when it goes wrong, it looks a bit like this. This is somebody having an epileptic seizure. So we know that electrical activity exists, and when it goes wrong, you get all these problems. Okay, so I don't know if that is a good place to stop for today. It might be. So I have a few other things that I wanted to say today, but I think it might actually work better if I say that tomorrow. That's probably to do more with the idea of action potentials and membrane potentials and how electricity communicates from one to the other. So this is really about the history of how we got to a stage of being scared and being panicked to where we are now. And that really came about because of people being curious. What is going on here? Why? And trying to understand what goes on, trying to think of ways to answer those questions, and search for rational truths that we can understand, not a truth that is based on some kind of magic or supernormal phenomena, supernatural phenomena. These are rational truths. I can see it, my own senses can see it, and I can share that with you. I can demonstrate that it is the rational truth to somebody else. And also building on people who have gone before. You overcome the awe and fear, and you set aside dogma, and that's how you make progress. So that's a little bit short. It seemed like a natural place to stop. So I thought I might just maybe take questions, and if there is further interest in any of those topics, we can go back and maybe talk about a few of those things. How about that?
Yeah, that's fine. Yeah.
I did have a few more slides in that section, but I don't think it fits that well. So I'll probably move that to the second part, if that's okay. What do you think, kids? What did you think of that so far? Have you learned about action potentials and membrane potentials and things like that? Anybody?
No, sir.
No. Okay. So this will be a little bit new. I think that's probably 12th stuff, maybe.
Some of them are going, when they tell they are 11th, I think they have just gone from 10th to 11th, I think.
Yeah, sure. Yeah, I think this is something that you're going to study in your 11th, maybe. Where does electricity come from in the cells? And how does that enable the brain to work? That I was going to do a little bit of that. Maybe we can, but we'll see if there are any questions. So what do you think about that so far?
I saw neurons and synapse in the 10th standard books of my son's school.
Oh, did you?
Yeah, state syllabus.
Okay. So maybe, if you're familiar with the idea of action potentials, we can talk a little bit about that. We'll revisit that next week maybe. But essentially, every living cell has a bit of electricity in them. Did you know this idea that a cell has an electrical charge? Every cell has it. Yeah. The electrical charge is really the difference in the. Okay, what's in the chat? You didn't know that, Aksa. You didn't know that. Okay, so fundamentally, every cell has a what is called a membrane potential. Okay, you know a cell has a cell membrane, right? You know that. That's, I think, year 8 biology. So there is a membrane, and the membrane has the inside of it is negative in relation to the outside, and that's how animal cells are. And how is that negative potential achieved? You pump sodium out of the cell, right? Sodium ion is Na+. It's a positively charged ion. You push that out of the cell, and then the inside becomes negative. And so it is achieved by a thing called a sodium-potassium pump, which sits on the cell membrane and is constantly pushing sodium out of the cell and potassium into the cell, right? And so potassium is also a positively charged ion. It's K+, but the sodium-potassium pump will pump 2 sodium ions out of the cell and 1 potassium ion into the cell. So it's on a 2-to-1 ratio. So as sodium goes out, 2 sodium ions go out, only 1 potassium ion will come in. And over a period of time, you have more positive ions outside than inside. So the inside becomes negative in relation to the outside. So that's the membrane potential. And it is one of the earliest evolutionary features of life. And I'll talk a little bit more about that. And this potential can be changed by allowing sodium and potassium to go in and out of the cell through these special gates called channels. And when they open, they allow the sodium, which is outside the cell, to come into the cell. And then the inside is no longer negative, it becomes positive. And that is an alteration of membrane potential. And it can be changed by the voltage of the membrane itself and special chemicals called neurotransmitters. And we'll talk more about that next week. But I just want to talk a little bit more about how this stuff actually happened. How did life start? What even is life, really? And it probably started, we don't know for sure, but probably about 4.8 billion years ago in the depths of the ocean, where there is very high temperature, very high pressure, and a highly alkaline medium. And these conditions have been recreated in the lab. You can get conditions that results in this process called carbon fixation. Anybody heard of carbon fixation? So carbon fixation is a process of converting inorganic carbon into organic carbon. What's the chat? No. Okay. I think probably studied about carbon fixation in pre-degree. So I think 11th or 12th, you'll probably come across this idea of carbon fixation. And carbon fixation converts inorganic carbon into organic carbon, and we are all carbon-based life forms. We are all made of different organic compounds which has carbon in it, and that is a whole basis of this thing called organic chemistry, is carbon-based chemicals, and they are monomers, so they are simple molecules, and then over a period of time they develop into polymers. So these are biological molecules which have the inherent ability to replicate. They divide and they make more of themselves. So that is probably fundamentally what life is. Life is the ability to replicate, to reproduce, to make more of itself. So that's free living, probably RNA and DNA, which was replicating. And then it became more specialized. So apart from just having a bit of DNA that was replicating itself, it got together with other things that could do other things. So like mitochondria could make energy, ribosomes could synthesize more proteins. And then all of those processes got wrapped up in a cell membrane, and then life became free living. It became a free living cell. And that is where, so this is called abiogenesis. So essentially from a chemical soup, from mixture of chemicals in the right environment, you get life forms emerging. So this is the birth of biology from chemistry, if you like, a form of, so it's one of the earliest evolutionary features. So when cells became free living, it had to maintain that environment of the cell. And the idea was to try and push, keep the, it's happening in the depths of the ocean. And the sea water had to be kept out of the cell. And it did that by pumping out sodium. Okay. So that is still the case. And when life emerged from the ocean onto land, we carried on doing that. So in fact, all our cells are still bathed in seawater. Yeah. So that's why all of our body fluids taste salty. Your blood, your tears, everything is salty because we carry the sea in us still. And this business of pushing sodium out of the cell and maintaining that potential difference with the outside in relation to the inside of the cell is the way every cell stores energy. This is ubiquitous, it's everywhere in nature, and that's how energy is stored. So every cell is essentially a small battery, okay? And this then results in this potential difference between the inside and the outside, which is negative on the inside, positive on the outside. So that's the cell membrane, and these blue and yellow things are the channels, which are in the closed state. And if you measure the potential between the inside and the outside, you can see that it'll be about minus 70 millivolts. That is how you measure that. And so that's a sodium channel, that's a potassium channel. And when they open, when they open, you create this reversal of electrical charge, and that is called an action potential. It's called the cell firing. And that this then produces an electrical impulse that travels right through the cell and goes to the end of the cell and can then affect other cells in its vicinity. So that is the way electrical activity is generated. And right. So Meryl says, I'm studying in Kuwait and we have learned about action potentials and resting potential in 11th bio. Right. So I don't think everybody's in 11th yet. Are you a year above these people, Meryl?
No, so I'm in 11th.
Okay, how about the others? The others maybe not familiar with the idea, maybe. So that's the idea that cells store energy in this way, and then we have this idea of action potentials being generated. And this is the last slide for today. Essentially, this was the experiment in the 1950s by these two people, Hodgkin and Huxley, in Cambridge, who identified exactly how the membrane potential and action potentials are generated by doing this technique called patch clamp on a giant squid axon. So this is a neuron, but it's a big cell. You can see it with the naked eye. You don't need a microscope, and you can then do very specific things to various channels. And they worked out exactly how that is that the membrane potential is generated, and to the point that they were able to write down the mathematical equation for that cell based on the conductivity of the various ion channels, and they won the Nobel Prize. So this is how science progressed from not knowing anything about what is going on in the brain to a level of understanding of brain cells where they could actually write down the mathematical equation for it. So I think I'll stop the actual presentation and I'll stop sharing my screen. Right, so what do you think of that? I think we are a little bit over time, but I mean, I was not sure exactly where to stop at that point. But anyway, and so any questions, any comments, criticisms, complaints? What do you think? What does a neurophysiologist do, Alina? So a neurophysiologist, it's a pretty broad term, neurophysiology. So neurophysiology just means studying the physiology of the nervous system. Now, you can study the neurophysiology of animals, and that would be to dissect the brains and take out the neurons and study what happens with the generation of action potentials and how that can be modified by various chemicals. So you can try and develop medicines for various reasons, various neurological conditions. But you can also be a human neurophysiologist, where you study electrical signals coming from the brain, either by using that EEG that I showed you, or there are other ways of doing advanced MRI scans, for instance, that can tell us exactly what's going on in the brain in various states, during sleep, and when you're awake, when you're happy, when you're sad, when you can remember, when you cannot remember, all of those things. So that's studying the physiology of some of those processes. So, yeah. Right. Alvin wants to know, how did you end up in the UK and how did I become a neurologist? Well, it was not a planned thing. I just, it was a career option that a lot of us considered back in the day. If you qualified from a medical college, you either did postgraduate training and became a specialist in India, or you went to US or UK. And I just ended up coming here. I can't remember exactly how it happened, but it was one of the things that a lot of my friends did. So 10 people from my year of 100 came to the UK. And I had a bit of an interest in neurology because it was just really interesting stuff. And when I came here, I eventually worked my way through the various junior doctor stages and ended up doing this. How does the positive ion move down when impulse pass? Right, good question, Arthur. I'm going to I'll talk more about it next week. But essentially, the positive ions they are outside the cell mainly, and when the channels open up, they rush into the cell. So it's mainly the sodium channels, the sodium ions, and then the membrane potential, which is normally negative on the inside, becomes positive on the inside for a very brief period, and then so that's called the action potential. But almost immediately, the sodium channels close, the potassium channels open up, and all the potassium is again pumped out, and that then rebalances that and brings back the resting membrane potential. So that's how that works. Okay. Everybody has different interests. Are they inborn? Well, yeah, we've had these questions before. How do you become the person you are? You're interested in different things, you're good at different things. It's a combination of a large number of things, and we can say it is nature and nurture. Okay, so there'll be some factors that influence how your brain develops that you inherit from your parents. That's genetic, and those things are there from before you're born. But at the point of birth, your brain is not really that developed. You just look at a baby. The baby can't do anything. The baby is completely dependent on its parents to survive and to grow. So a lot of brain development happens after birth in the first few years, and that's why human beings had to spend such a long time, relatively speaking, to other animals in their childhood, in their development stage. And during that time, you acquire various skills, and whatever you are exposed to at an early developmental stage of your brain growth, so when you're a young child, that will affect the way your brain develops. So if you start learning music as a child, then you become a very proficient musician. Even if you don't have a great deal of, your parents may not be good at music, but you can't train your brain in that way. So that's why, we ideally should try and develop. That's the whole point of this, is that we need to be able to expose our children to a wide range of things, so their brain has the best chance of developing in all different ways. And it might be that, you're going to be a great musician, but if you never get to play a musical instrument when you're young, that part of your brain really doesn't get a chance to develop. Same with sport. So acquiring a motor skill, like playing cricket, hitting a cricket ball that's traveling at 90 miles an hour, that's a skill that has to be ingrained in you. And if you don't get a chance to play cricket, you never know how good you're going to be. But if you start playing it at a young age, your brain develops in a way, and it eventually may turn out that you are actually better than anybody else in the world at that. So you've got to have a wide range of experience in order to give your brain the best chance to develop in whatever it is going to be good at. So that's really the whole point of a rounded education and a rounded upbringing for all kids. Aksa, does that make sense? Aksa?
Yes, sir. Thank you.
Very good. Good. Any other questions? So Meryl is asking, where can we find information about these classes? It'll be on the GrainEd website. That's probably the best place to look. Good. Anything else you want to ask, guys? So next week, I'll talk more about what the brain actually does in terms of the movement, the memory, the emotion, speech, and various other things. And then we'll talk about how that can go wrong and how we can try and fix that and things like that. Okay, very good.